We're continuing to talk about the Kalman filter, and today we're going to talk about the estimation and prediction process, and then hopefully get to some MATLAB examples. And my approach is that you don't need to know all the details of the derivation of this to use it. So there'll be a lot of expressions where we just go, hey, that's just the expression for that math thing, and whatever, move on, just use it. I'm going to show the Kalman filter algorithm again. We've got a prediction step here. Talk about that second, I think. So this has Roman numeral 1, the prediction step. What's going on? We're trying to estimate a state that we'll call xk. And if the subscript k bothers you, ignore it. All that means is that we're sort of marching through time, and k is at time tk, if you want. Xk is the state. We don't know it. Our best estimate is what we call this thing xk with a little hat over it, because we don't know it. And the assumption is that the true value is given by some normal distribution. That's what this n means, with the mean of xk and a covariance given by that pk. So that's one of the things that the Kalman filter does. It's basically giving you a normal distribution at each time step for what the estimate is. So we'll say more about that prediction step. The prediction step involves this thing that it says is xk hat minus. The minus means this is before actually taking in the measurement. So that's why the little strip minus. So that's the prediction. We'll talk about the prediction process. This part down here is the estimation process. So that's 2 through Roman numeral 4. What goes on here? This is when we spit out we take in the measurement, we use the prediction, and we spit out an estimate, both of the actual state and what the new covariance is. So how is this normal distribution changing in time? And there's some parameters here. This might be hard to see, but there's an A and a Q that show up just in the prediction step. Those are part of the model that we prescribe, mostly A. That'll be related to whatever process we're interested in. Like, for example, if all we're doing is measuring position and we want to estimate velocity and everything's noisy, we don't want to just sort of take a derivative of position. We could use the Kalman filter to estimate velocity from position, and vice versa. You could estimate position from velocity even when things are noisy. In this estimation step, there's a couple of other matrices, H and R. H is just related to how the measurement relates to the state we care about, and then R and Q are similar in that they quantify the noise. And that's the one that we'll know the least about. And you can kind of tune those. They're diagonal matrices, and you tune those to get better performance. Calibrate it. All right. That's the big picture. We're going to go through estimation first, and then prediction. And there's more advanced courses if you wanted to go into dynamics control and estimation, where you could find out where the Kalman filter really comes from and derive it. But you don't need to use it. So let's talk about the estimation step. All right, so the estimation step, we're doing computation of an estimate, xk hat, and this is, xk is an n by 1 column vector, column matrix, and it corresponds to time tk. So we're always marching from tk to tk plus 1 and so on. And maybe these are equally spaced in time. They don't have to be. So it was part of what we wrote up there in the estimation step. Kind of the heart of it is this, where it takes in xk hat minus from the prediction, and then plus this gain multiplied by the measurement minus h x k minus. And how can we interpret this? This is this h times xk minus. This is called the predicted measurement. So notice we're subtracting the true measurement from the predicted measurement, and then that's all getting multiplied by this Kalman gain. Like how much do we put on that to update our prediction? All right. I'm going to rewrite this so that it looks in a form that might be more familiar from some other stuff we've done. So xk equals, I'm just going to do this matrix multiplication. So this is Kalman k times zk minus Kalman times h xk minus. I'm going to group the xk minus terms, so it looks a little different. So this is all going to be multiplied by xk minus. I'm going to have a matrix here in front. So it's implied that if I just have this vector by itself, there's the identity matrix, and then I subtract x, k, h. And then there's this other part. Now, in reality, h is related to how the measurement and the state are related. But for now, just to make life easier, we're going to assume that we don't have a matrix. We just have n equals 1. And h is just 1. And that's okay. It doesn't really change the argument I'm going to make. So if I have that in there, then this is xk equals 1 minus k at time k. xk minus plus k times that. Now, if we substitute alpha, we'll just substitute this symbol alpha for 1 minus k. So, okay. Then this looks like it's k equals alpha. It's k minus plus 1 minus alpha zk. This is from the Kalman filter, but hopefully it should look like something we talked about, that first order low pass filter. So let me just put down here the first order low pass filter from last time. And you notice they look somewhat similar. And that was just the whole point of this, just to show that the Kalman filter estimation process, it looks like a low pass filter with a dynamically changing weighting alpha, or equivalently a dynamically changing gain k. So that's kind of the upshot here. Kalman filter estimation process is like a low pass filter with a dynamically changing alpha, or equivalently that gain, the Kalman gain. All right. If I haven't said that it's called the gain, it is called the gain. Remember from before, we, as the designer or user of the low pass filter, we got to pick alpha. It wasn't picked for us. Here, the Kalman filter kind of picks it for us. So that's nice. We don't have to think about it. So in fact, the gain gets updated at each time k, according to an expression that I'm not going to really say much about, but it involves this covariance thing, the predicted covariance, and then I think this is H transpose times H PK inverse HT plus R. And that's the inverse of that whole thing in parentheses. So this is part of the dynamic updating of the gain. The error covariance also gets updated. And then this goes into the next time step, and it's just, you just sort of loop through. So this takes the predicted, and then this thing gets subtracted off. And I won't discuss where these come from. Let's just say it works, and it's smarter people than us have worked on it, figured it out. I could give you an idea of what the error covariance means. Or maybe you don't care. I don't know. I'll tell you anyway. The error covariance, it's a measure of the inaccuracy of the estimate. I say that as opposed to accuracy, because as the error covariance is larger, you've got a more inaccurate estimate. So if you've seen a normal distribution, right? The assumption that goes into the Kalman filter is that there's going to be noise, and the noise is Gaussian noise. And also the true state at that time step is given by, and this n just means normal distribution with a mean of xk hat and a covariance pk. So xk hat is the thing that gets spit out as the best estimate with covariance pk. This is related to the spread of the bell curve, right? So what's going on here? If I were to make a little sketch, this is xk, the true state that we don't really have access to. There's a mean, and then you just kind of do a dashed. There's a bell curve around the mean. So the true value, the best estimate is that it's going to be the mean. This width is related to pk. If pk is large, then the error is large. And I'll just put large in quotes, or the error is possibly large. We don't really know. If pk is small, then the error is small. So error being small would mean that we have a tighter normal distribution about the mean. So this would be, as I've drawn it here, this is lower error, and then this is a higher error. Hopefully that makes sense, even if you don't know much about normal distributions. And I think I mentioned it before, but two matrices show up here. Is it in all of the steps? Yeah, there's a H. Things that come from the model, the system model that we will provide. The Kalman gain is computed as part of the algorithm, but H, which is here and also R, these are matrices that we'll decide as part of our best idea of what the model is for our system. So there's H there. So this is just a note, H and R only show up in the estimation step, and they take in something from the prediction step, which is what we'll talk about next. And there's all kinds of variations on the Kalman filter. So all of these assumptions I'm saying are for the very simplest Kalman filter. Other things could assume other types of distributions. That's where there's other names like extended Kalman filter, scented Kalman filter, unscented. People have written multiple PhDs about different types of Kalman filters. So let's talk about the prediction step, which, at least in terms of that diagram we had before, comes before the estimate. So this spits out something that then goes to the estimation process. So let's write what's the computation of the prediction. So we've got xk hat at time tk, and we're trying to give a prediction of what xk plus 1 will be. You want to predict at the next time, tk plus 1. And what we have for the algorithm up there is xk plus 1, or it's equivalent to this. You might be worried, like, well, hold on, you wrote it as xk in terms of xk minus 1. This is equivalent. So at xk plus 1, this minus up here means this is the prediction. We expect this will be some n by n matrix A times xk. So A is an n by n matrix. And p k plus 1, the prediction of that, I could write the formula, but it will make little to no sense to us. Yeah, I'll include q. There we go. And just to summarize something here about the estimation step, right? We've got the estimate of the error covariance, prediction of the error covariance, estimate of the state variable, prediction of the state variable. What is this Q? This Q represents, it's sometimes called process noise or state transition noise. This thing up here, xk plus 1, that I said is the estimate. Some books and some people will call it an estimate. Others will call it the a priori estimate, meaning before we take a measurement, this is what we expect. And then once we've taken a measurement, it's called the a posteriori. It's not something I want to say much. And what will you notice? A and Q are here. Note A and Q are only in the prediction step. They don't show up in the estimation step. So then these predictions get passed to the estimator, and that's that. All right. To try to kind of solidify this in our minds, I could give you an idea of what's the how prediction and estimation kind of fit together. And to do that, let's go back to the low pass filter, just sort of diagrammatically show what the low pass filter does. So that low pass filter, we wrote it as xk equals some constant alpha times the previous estimate plus 1 minus alpha of our new data point, xk. So it's got some idea of how to incorporate the new data point and also the previous estimate. In terms of a diagram, this is showing that at a time, say tk minus 1, the low pass filter algorithm took in the previous estimate, x bar k minus 2, incorporated the new data point, and then gave us this new estimate, which then just gets passed as is to the next time step, where then we incorporate this new data point and get a new estimate. We can compare this with the Kalman filter, and it's going to look a little bit different. So xk, x bar. So the best estimate, k, is xk minus plus the Kalman gain, zk, the measurement, minus h xk minus. Now, what have we assumed for what xk minus is? We're saying this is A, whatever our A matrix is, times the previous estimate. So I'm going to substitute that in wherever I see xk minus. So wherever I see this prediction, I'm going to put the formula over here. So xk equals A x k minus 1 plus this Kalman filter, the Kalman gain, z k minus h times a x k minus 1. All right. So this is trying to diagrammatically show the Kalman filter. What's going on here? Well, at this time step, tk minus 1, we've taken the previous prediction, and then there's a measurement. So this z k minus 1 being incorporated in, this is taking a measurement and then getting the estimate. And this is our best estimate at that time step. And now the difference between this and the low pass filter is this doesn't just get passed without changing over here. What we have at this point is this formula. So the new prediction is A times this. So this is the prediction step. And then again, there's a measurement, a new measurement. So these kind of curving arrows are the estimation process, taking in the measurement, giving out the new estimate, and then this just goes forward on and on. So that's kind of diagrammatically how they fit together. So the things that are left unknown, that aren't specified by the algorithm, are these variables that we'll call the system model. And this is just the problem expressed in mathematics. In particular, those matrices, A, H, Q, and R. In general, they're matrices. And I'll give you all of the dimensions. The Kalman filter, the basic Kalman filter, it deals with a linear state model. And this is very common in modern control theory. So let me write this out. We're assuming that the process going on that we're trying to get the best estimate for, so there's no hats or anything here, that xk plus 1 equals A times xk plus noise, which in the state, we'll call that wk. So we have a linear process plus noise. Linear means this is just a matrix times that, so it's linear in the old state. So linear plus, I'll either call it process noise, or because that's easier to say, or state transition noise. People use different terms for that. The measurement, zk plus 1 equals H. So this is where H shows up. So it's just the matrix H times the previous state plus VK, which is the measurement noise. Linear plus measurement noise. Like if you have a very highly sensitive temperature gauge, you'll see it wiggling, and that's probably measurement noise. Process noise is something else. Process noise is the noise that you can't get rid of even with perfect measurement. So it's kind of representing just the uncertainty of the world. Wow, it's super helpful there, Dr. World's uncertain, huh? Thanks. All right, so let me give you the dimensions of all of these things. xk, this is the state variable, and it is a n by 1 column vector. Zk, the measurement, doesn't have to be the same size. So we're going to say it's m. So you could have m different measurements. So this is an m by 1 column vector. A is it's called the state transition matrix. Some people might call it the linear process matrix. I don't know. It's an n by n matrix, so it's a square matrix. H H goes from the state, takes in the state, multiplies it, and spits out the measurement. So we can call it the state to measurement matrix. And it will be M by N. And then WK and VK, what are those? This is the state transition noise. It's the hardest one to understand, so we're not going to understand it today. And it has the same dimensions as the state variable, so n by 1 column vector. VK is the measurement noise. That one's a little bit easier to understand because usually the manufacturer of a sensor has done something already to tell you, here are the error bars. It's going to be this plus or minus something, and that's related to this measurement noise. So this is M by 1 column vector. All right. So those are all the things. I think it'll make more sense once we start doing an example. Before we do that, we've mentioned two of these matrices, A and H, but what about Q and R? Q and R are related to the two noise terms. The covariance of the noise. Q is the covariance matrix of WK. And this is an N by N diagonal matrix. So it just has entries along the diagonal and everything else is zeros. So that's the covariance matrix of the process noise. R is the covariance matrix of VK. So that's M by M. Diagonal matrix. So if N is, greater than 1, then WK, we could write that as WK first entry, WK the second, all the way down to WKN. So this would be the noise in XK, the first entry. This would be the noise in XK, the second entry, all the way to, this represents the noise in the nth entry. And we'll describe those in terms of variance. So let's say the variance here is 1 squared, or sigma 1 squared. This is sigma 2 squared. This sigma stuff is typical for representing variances. So these are the variances. So sigma, I'll just say I, is the standard deviation. I'm more used to thinking in terms of a standard deviation, but then when you square that thing, that is the variance. If you're reading something about the expected noise or error is this, and it gives a standard deviation, you actually have to square that to get the variance. Okay. So for example, what would Q be? Q would look something like sigma 1 squared, sigma 2 squared, everything along the diagonal, sigma n squared, and everywhere else is zeros, which I think MATLAB knows how to take in if you write diag sigma 1 squared all the way to sigma n squared. It'll produce this diagonal matrix. And similarly for R, I've said some things about looking at like what the sensor itself says is its own error, but often these things, these sigmas in both Q and R are found by trial and error and calibration. Fine by me, right? There's probably some other approaches you could use to make trial and error go faster. But really, you could just think of those as knobs you can turn. and it comes from trial and error. If you know ahead of time, oh, I expect large noise, it's not like the Kalman filter won't work. You just get better performance if you have these closer to the actual error, actual expected error. So it's probably better to overestimate the error and then just see how the Kalman filter does, and then you can start changing. But, yeah, and I guess the note for R that I've said a few times is sensor specifications can sometimes give you that, can give R as well, the entries of R. So if you were told something like the position error, it's plus or minus 2 meters, let's say, then that would mean the standard deviation is 2. So sigma squared is going to be 4. And then I guess it's understood the units are meters squared. This stuff about the noise is probably the hardest because it, trial and error. Sounds like guesswork. And yeah, it is. So that's that. Are we ready to try a simple example so that things can kind of make sense, hopefully? Let's do that. Sometimes error bars are presented as a percentage, and you could do that. You could have different, I don't want to get too much into it, but Q can be different at each time step, but let's not do that. All right. So let's look at a simple example. And I'll use the voltage example that we did last time, where we used we just calculated the average in a recursive way, voltage estimate from a battery. And we expect that, just like last time, the voltage is a constant. The true voltage, which let's say we don't have access to, we only have access to our measurement from our multimeter or something. So similar to last time, voltage is a constant, but our measurement is going to be fluctuating around it. So our measurement, this is to construct the model, and constructing the model means coming up with those matrices A, H, Q, and R. That's all we're trying to do here. Measurement, so that means the Z thing, measurement is voltage and has noise. X, the state, is also the voltage, just the voltage. And we'll assume that there is no noise in the actual unknown to us voltage. So we've got from this, at least the measurement is just one scalar variable. So M equals 1 and the state N also equals 1. Let's write what we think our process is. X plus 1, we think is XK. The voltage, the true voltage from one time to the next shouldn't be changing. So this is our model. Voltage stays the same. What about Z? The measurement is going to be, we think, equal to the state plus some noise. Measurement is the voltage plus measurement noise. Now let's translate this into matrices. What's A? Well, if this is supposed to look like how it should, this would be xk plus 1 equals A xk. So what is A? A is an n by n, so that's just one, it's just one scalar. A equals 1. What's H? This would be zk equals H times xk. And it's an m by n matrix. So it means 1 by 1. It's just another scalar. H equals 1. Now the noise stuff, I guess I am assuming that there's no noise in the state. So no noise in the process. So I'm assuming that Q is 0. Remember, 1 by 1, it's just a scalar. And I'll assume something for R. I'll say 4, just to give me something. Which means I expect whatever the measurement is, it's going to be the true measure, the true. And then this will be sigma equals 2. So there's going to be something that's plus or minus 2, plus or minus sigma, because 4 is 2 squared. What are the units here? Volts. Now, another thing that was the beginning of the diagram for the Kalman filter was you need to give it an initial guess. Sometimes, I think usually the initial guess doesn't matter. It just sort of speeds up your thing. Maybe, and usually you get this from experience. So from experience, we've seen that the voltage is around 14. So that'll be our initial guess. I guess we can call it an initialization guess. So X, the predicted, just to initialize the algorithm, is that we think it'll be close to 14. And we don't know what the uncertainty is. We'll assume something big. We'll say 6. So now we can code this up. Negative means that's the prediction. So if I were to go up here to the top, this is what I'm looking at. You set initial values and then it goes into this. But after this setting initial values, you never use those again. They just help initialize it. Yeah, no problem. All right, so let's try to code this up. I'm going to be doing this one called 10 simple Kalman. I don't think we'll get to the other one today. So this simple Kalman is, let me go to simple Kalman. So this is showing, we're defining these things that are the persistent variables, meaning they stay only within this function and it remembers each time you call the function. When you first call it, there is no first run variable, so that's empty. And so this initializes things the first time you run it. So this is saying A equals 1, H equals 1, just like we determined. Q equals 0, R equals 4, and then our initial guess, X is 14 and P is 6. And then this thing's writing first run equals 1 just means this will never be called again. Yeah. I just wanted to pick something big. Is that so the larger this is, the more uncertain I am. Like, I don't know, it's 14 plus or minus, say, square root of 6. Ooh, and I already wrote this. Good. So here's the Kalman algorithm just written in MATLAB. So XP, that's the prediction. This is that step 1, prediction of the estimate. And then PP is the prediction of the error covariance. Remember, it was A, P, A transpose plus Q. And then, so that's the prediction step. And then there's the 3 parts of the estimation step. We compute the Kalman gain, which we have absolutely no insight how this is working. We could maybe think about if R was big and Q was big, how would this influence things? But for now, it's a black box. It just works. It's a way of updating at each step. So this is the K at this step. And then here's the computation of the estimate for the state. So maybe I'll write state estimate. And there it is. And then computation of the error covariance that then goes into the next part of the process. We could even later pull out these things like the gain and P to see how they're changing in time. Remember, I gave an initial guess for what I thought P was. I thought P is 6. If that's going down with time, that means the Kalman filter has more and more confidence that it's getting something true. Remember, the Kalman filter doesn't know that the voltage should be constant. And I guess I should show that part of the algorithm. Here we are testing. This is all the same as before. It was 0.2 seconds between each measurement of voltage. And we keep calling this thing called get volt. What does get volt do? It just spits out a measurement, which is 14.4 plus this noise, which is actually has a standard deviation of 4. But so it's going to look very jagged, and hopefully the Kalman filter can handle that. So unbeknownst to us, the true value is 14.4. Let's see what the Kalman filter can do. So all we do is run this, and then it'll plot some stuff. And I throw in all these things just to make it look pretty on the plot. So if I run, there it is. So at first, it's the Kalman filter is doing really bad, but then it seems to be doing pretty well. It's pretty close. Even though this is fluctuating wildly, it's getting something that seems pretty close. I honestly do not know the theory of this, if this will like converge to the true value after long enough time. I don't know. I just know it's useful, and hey, it gets pretty close. So I have another code here that'll give us it'll spit out, it's this thing called simple Kalman 2. Instead of just spitting out the voltage, it also spits out the estimate of the error covariance and the gain, Kalman gain. So we can call that, you can kind of see down here, it's just spitting out some extra stuff. Let me run this. This one's called test simple Kalman 2. And maybe I need to close all. Clearing everything is always a good idea. Here are all the variables. Okay, this has produced 3 plots. The first plot is very similar to before. Now, every time I run this, it's going to be doing a new set of random measurements for the voltage. But it looks like the Kalman filter is getting pretty close. This says 14.1. This is for the error covariance. So my initial guess was 6. Like I had no confidence. And this is saying as time goes on, it's way more confident. I don't think it'll ever go to 0, but it's getting more confident that the error is going down. Here, this is showing the Kalman gain. And notice this is going just between 0 and 0.6. This was just internally calculated. Both of these were internally calculated. Right? And notice the gain is going down and down and down and down and down. Remember, the gain was equal to 1 minus alpha. So as the gain goes down, that means alpha, in terms of the analogy with the low-pass filter, is going up and up and up and up and up. You can mess with this, play with this. This was just supposed to be a simple example because we did tell it ahead of time with a equals 1, it was constant. If we had a different model, let's say we're trying to estimate something that could be changing in time, like the position, and maybe we want from the position, we want to filter that out, get the more precise position. The Kalman filter is so flexible, you could do things like from just measuring position, also estimate velocity. So I'm going to set that up. I don't think we'll actually get to compute it, but we can set it up. So hopefully that part of it gave you some insight as to how this is supposed to be working. From the simple example. Now we'll look at something more complicated, but not that much more complicated. Estimating velocity from position. And we're just going to be doing this in one dimension. So we're taking a one-dimensional measurement. So m equals 1. We're just getting position. And we could apply this to something like that sonar altitude data, so that not only are we getting a more precise estimate of the altitude, but we actually get an estimate of the velocity. And how can we do that? It's because position and velocity are related through a linear state model. Let me show you how that works. So let's set up the system model. We're trying to get velocity and position, which means n equals 2. And here's how it works. X, say at time k, and I'll just use words. It's the position and the velocity. at time k. And we can set up how what the linear process is. X at k plus 1. So at the next time step, we expect this will be, well, according to the process model, we have to fit something into this sort of mathematical framework. X k plus 1 equals a x k. Z k equals h x k plus b k. Leave these things, forget about them for now. Who cares? Focus on the parts that make more sense. So A, we know that A, since n equals 2, A should be a 2 by 2 matrix. And I'll just tell you what I think it is, and we'll see if it works. I think this is 1 delta t 1. The time step between measurements is delta t. So this delta t, if we were measuring, I think for the sonar, I said the measurement time step was 0.02 seconds. So that would be what we would use here, 0.02 seconds. I claim that's A, and I'll claim that H, which should be M by N, so that means 1 by 2, is 1, 0. So this is a 1 by 2 matrix. This thing over here is a 2 by 2 matrix. So far, so good. So we got the dimensions right. Does this seem to fit? Let me say, again, xk plus 1 is the position and velocity at time k plus 1. According to this up here, it should equal a 1 delta t 0, 1 times the position and velocity at the previous time. And we're just sort of ignoring noise for now. If I do this matrix multiplication, what do I get? I get that for the position, I'll get a new 2 by 1 column vector, and this will be the position at time k, so I'll just put a subscript k, plus delta t times the velocity at time k. That should be an estimate for what the position is at the next time step, right? Because the distance traveled between k and k plus 1 is the time, delta t, times the velocity. So this is how, we know the relationship between position and velocity. And then this 0, 1 just means, since I have no information about how the acceleration or anything, or I don't want to, I don't want to estimate that right now. So it's velocity time k. Does that make sense? So that's A. A seems to work. This is the new position. It gets updated from delta t and the old velocity, and then the new velocity is similar to the old velocity. It's our best guess. Yes. Yes. Yeah. So if I wanted to estimate acceleration and velocity from position, then I'd have a 3 by 3 matrix with all kinds of things. Yeah. But I'm just stopping at velocity. So yeah. So delta t would be like 0.0, for example, 0.02 seconds for that sonar altitude data that we looked at last time. All right, what about Z or H? I said H is this. Why did I say that? Well, let's just see what it gives us. ZK equals H xk. And here I'll keep the noise because there's going to be noise. I said H is 1, 0 as a row vector times position time, both of these are time k. So position and velocity is the state of time k plus some noise. If I do that matrix multiplication, right, what do I get? I just get position back. So that's because I know that I'm measuring position. So it looks like we've got our matrices. We've got A, we've got H. The noise stuff, noise is, I don't know, maybe you could say it's harder. It also, I think, affects the result less. I'm just going to say as an example, and we won't be able to do the numerics today, but I'll use Q, remember, has to be 2 by 2. I'm going to say I know the position better, so that's 1. And this Q comes from the process noise. So from my point of view and your point of view, these are just utterly made up. Okay, so it's, yeah, just utterly made it up. R is related to the measurement noise. And maybe I know something about this sonar system I'm using. And I know that it's has a large error. So I'll say R equals 10. There we go. So next time, we'll do the MATLAB example using the sonar data, and we'll try to get velocity from the position. And the nice thing about it is this would be the preferred way if you're actually to use this for some kind of control. You don't want to be taking derivatives of very jagged, noisy things. You want to use something like this. So that's how the Kalman filter gets used.
If you appreciated this video, please like and subscribe, or just wait and watch the next video in the series. There are links and other materials in the description.